Hello everybody. So now we will go for the next step, which is the solution of the problem. So now we will see how the concentration will be changing with distance according to the inputs that we have. So to solve, either to go to the this solve drop down list and say solve partial differential equation, or to click on this button, which is push to solve, what it says in the bottom. But before I solve the problem, I want to take a look at this first, this option, which is the properties of the plot, because this is gonna be very important. This gives us a lot of options that are related to the how I show the results. So the basic and the very basic thing is to plot the concentration as a function of space in the form of colors. So if I keep this option and I click plot, this is what I see. So I have here this bar. It says that the color is 0.1 is the purple, and the 0.001, which is the minimum concentration, is the light blue. So this is what I see, that there is the light blue in these two sides, because these are the points where I have, or the sides where I have the concentration is constant. The same for these two sides where I have the concentration equals 0.1, which is the maximum value here, and the transition takes place in the z and in the radial direction. And this is what I expect based on my inputs from the information I know about the problem itself. There is one option here that is, I think, will be of interest to many people, which is the colors. So the software gives you the option to choose different color maps. So this is the first option, which is the cool option. Then you can choose it to be gray, so it's gonna be different shades of gray color, from dark gray to light gray. You can make it pink, you can make it copper. There are many options here that you can pick from. I personally like this Priula option, which is blue, yellow, green color transitions. So this is the option that I have. So I have the yellow color here, and this is the dark blue color. There is what's called here for the same option, is called the interpolated shading or flat shading. So if you remember, we said before when we did the meshing that each area has, or is considered as, a constant concentration area. So the concentration is constant for the whole area. But what I have here, it doesn't show the triangles, it just shows the whole area and the concentration distributed within this area. But if you choose the and this is what the software does, it kind of smoothes the color between different or adjacent triangles, so that the color is kind of continuous. But if you choose the flat shading, you would see that this looks different. So it looks here the way it actually is, where each triangle has its own color, and you'd see the transitions from dark blue to lighter until it reaches the greenish color here. And this is why refining the mesh would make a big difference here. So if I refine the mesh and solve the problem, you'd see that these are the triangles. If you refine it more and then plot it, then you still see the triangles. If I zoom, you can still see the triangles. They are kind of hard to see here, but they are already there. So this is why the refining makes the quality higher, the quality of the solution, of course. But anyway, so let's go to kind of just one level of refining and keep it as interpolated shading and plot it. So the interpolation will make the colors nice here. There is an option which is called contour, and the contour is or the contour option will split the area into smaller areas. Each one has a homogeneous concentration. So here, this is what I see, that this area in the middle and this area here has a homogeneous concentration. So it's not exactly the same concentration, but it gives you increments. So I have here the concentration, the number of levels is 20, so it breaks the concentration from minimum and the maximum values from 0.001 to 0.1 into 20 increments, and each increment is put in the same area here. So if I want to make it 30 and then plot, then you'd see it's increasing the number of increments. If I make it 10 for instance, then it's breaking it into smaller number of areas. Anyway, so this is kind of a nice option here that you can see. One other option, which is a very, very important option actually, is the arrows option. And this arrows option is an option that lets you see how the flow goes, what is the direction of flow. So you can choose to, let's say, draw the flux lines as arrows and then plot them. So this is what you see here, but this is not very clear in this case, because we have a lot of them are just dots, and this is because I have the plot style here as proportional. And by proportional, it means that the arrow size, it's not just so the arrow does not only indicate the direction of flow, its size indicates the magnitude of the flux. So the flux is a vector, so it has a magnitude and direction. So you can do it in a proportional way, so that the length of the flux of the arrow represents the magnitude. So I have the maximum magnitude in the corners because I have here the maximum driving force 0.01 and 0.001 or 0001, I'm not sure. So the maximum driving force is in these corners, but the driving force decreases as you go towards the center, and this is what we expected here. But if you want to see the arrows without having this proportionality, you can keep them normalized, and this is what you see here. And I would like you to compare what we expected from our knowledge or understanding of the problem and what we see here. So this is almost the same. I expected that there is symmetry here, there is symmetry here, and the arrows will go down and left, down and right, up and left, and up and right, and this is exactly what we see. And you can clearly see this is an axis of symmetry, this is an axis of symmetry, so it's behaving the same way we expected based on our understanding. So this is regarding the arrows. You can have and this is what it says vector field, and of course you don't have values for the flux here, because the values that you have are the colors that are available here. You can pick another option, which is the concentration gradient. It's not going to make any difference because the flux is directly proportional to the concentration gradient, and the proportionality factor is the diffusion coefficient, so it's not going to make any difference. You can have the option to plot the XY grid. So if you do this, then you can show the grid within the plot, and I think it's not working for some reason. Maybe you can check it next time. Because I have to show mesh, so you can show the mesh as XY or shows the mesh as the triangles. So you can have many things displayed. Of course, having everything in the same plot will make the image not very clear. So I personally don't like to show the mesh, so I would prefer to go for the arrows and the colors because they are very, very informative this way. So for now, I'm gonna stop here, and there are some other options that we will check next time, which are related to the deformed mesh and the height of the 3D plot, and we can check the exporting the results and how can I get the results as numbers. So we will talk about this next time, inshallah. So I'll see you then.